Okay, again, my apologies for the video camera. It sure doesn't, I've got about a 2-inch window here that I can write in. Is pretty challenging for me, but we'll get that sorted out soon. And I'll do this lecture live again also, but I wanted to make sure that you had all this in case you're in a panic about getting the homework done early. Okay, I want to talk about Brewster angle. And in this case, we want to do the opposite of what a critical angle does. So I've got two media here, region 1, region 2, and I could give myself some more room this way maybe. Coming in at an angle with respect to the normal here, as it's called, theta incident, there will be a theta reflected that's the same as the incident angle. There are things called diffraction gratings that have little triangles and rough, little basically tilted mirrors here. This always holds locally, but if you have one of these gratings, it may look like you're getting reflected angles at other angles, but it's because somebody put some triangles in there, so we don't have to go there. All right. This always holds in some sense or another. And then I'm going to have some transmitted angle, call that theta t. And what I'd like to do is make it so that I don't have any reflection. Okay, so critical angle made total internal reflection. Brewster angle is going to be to make it so that there's no reflection. So that's useful. How on earth do we make that happen? Notice we have an electric field. It's a sine wave, and it's propagating along in some direction. Direction given by the k vector, and this on the y-axis here, I'm plotting the electric field. So I have some electric field, it's a sine wave, and it's going in the direction of this k vector. So it's propagating in this direction. The electric field itself is on the y-axis here, up and down, right? And it's going to excite the atoms to move up and down this way, or an electron within an atom. Okay, there's a force on the electron of charge Q is proportional to the electric field E. That's kind of an aside, so I'll put it in squiggly brackets. Right? But the charge jumps up and down in the same direction as the electric field vector. So these are called the electric dipole. From dipole antennas, which are wires in which the charge jumps up and down. Okay. I'll do this on the side. Maybe I'll do it. Save it for live. Yeah, I'd rather do that as a movie when I have a big screen that I know I can show up on. Okay. All right, so I'll do an aside later. Let's get back to this electric dipole. Looking down on the electric dipole, the charge just moves up and down, in and out of the page here, right? So one way of depicting that, kind of a vector, would be like an arrow. A Native American fires an arrow in the air. This would be the crosshatch of the part that I put my string of my bow. This would be a vector going into the page, and then the pointy part of the arrow coming right at me would be a vector coming out of the page. So for the electric dipole, this vector of the charge, the motion of the charge, is in and out of the page. I'm looking down on the top of the dipole as opposed to looking at the side view of the dipole. Okay. So looking at the radiation pattern, which is a contour of constant power, if I've got this wire of charge going up and down out of the page, and so I take my little power meter and I'll measure power equal to 1 watt. I'll walk around, I keep my power meter so that it always reads 1 watt. I'll walk around in a circle. All of the power at this distance is equal to 1 watt that I'm detecting. This is the way I measure a radiation pattern. Out here, the power is weaker, right? Because I've got the same size meter, my box, that lets in a certain amount of energy. This is a radio tower. This is my cell phone, for example. When I'm closer to the tower, I have more energy. I detect more power. When I walk away from it, the power drops off. So here I'm walking around to points where the power is equal to 1/2 watt. Again, it traces out a circle. It has to, because the source is invariant under that rotation, so it can't create anything that's not invariant under that rotation. So it's called isotropic. Right? All angles are receiving the same power. That's when I look down at the top. When I look from the sides, you see a different type of radiation pattern. You see that a lot of the energy is focused out to be out here. Right? And then as you walk around this direction, it goes down to 0 here at the top. So there's a null. Key point is here, the electric dipole charge is moving up and down this way. Right? They don't radiate any electromagnetic wave in that direction. Okay? So Brewster was clever enough to realize, bypass the math. I'm sure he didn't do it with the math first. Gotta have the idea first, right? So if I've got this wave coming in at some angle, and then set it up so that the transmitted angle is such that the nulls of those dipoles are exactly pointing in this direction of the reflection, then I can't have any reflection, right? The only reason I get a reflection is because the wave's interacting with the media, and the media then is re-radiating the wave. So this is air, this is glass, it's the electrons in the glass that are jumping up and down that cause the reflection in the first place. Set it up so that this can't happen, so that these dipoles have their null pointed in that direction, then I should get no reflection. Indeed. So to solve for what angle that is, you just do the math, which I'm not even going to bother with, but I'll sketch it out here for you if you want an equation for it. This transmitted angle will become the Brewster angle when this angle, theta t, plus 90 degrees here, this has to be 90 degrees for the null to point in that direction. 90 degrees is called pi over 2, is another name for it, radians. Plus, this is also theta I, right? Theta r equals theta I. And so all of that adds up to 180 degrees. Another name for that is pi. Go through Snell's law, and out pops the equation for the Brewster angle. I'll skip the algebra, but it's going to involve N1 2 and the sine of the, or I think it's tangent. Anyway, let's just draw the answer, right? So for one of these polarizations, right, and here are the names of our polarizations. We'll get back to that in a moment. For one of these polarizations, the one that would kick the dipoles up and down in this direction, right? So think about which, I'm not sure if I had that on the homework or not. I may have dropped it. Maybe I'll sneak it in later when everything's running smoother, so I know you're getting good quality videos. If the electric field is moving in this direction, then the dipoles are going to move in this direction. Then that's going to put the null in this direction, and that's going to give me a Brewster angle, right? So if the electric field was in the plane of the paper, then I can have a Brewster angle. Otherwise, the electric field is jumping up and down out of the page. I'm exciting the dipoles in the wrong direction, and I won't get a Brewster angle. Okay? So when I don't have a Brewster angle, the amount of reflection just keeps going up and up and up until I get to the critical angle, and then there's all of it is reflected. Okay? For this other polarization, and I think that is a question on your homework, just to make sure you look at the lecture notes here, right? And you can see it right, I see it right in front of me, the answer. But for one of these two polarizations, then I can have this Brewster angle, and the amount of reflection that I see will start to go up as I increase the angle. Then it comes down, I get no reflection at the Brewster angle. But again, as I go up to the critical angle, I have to get more reflection. Notice we never even mentioned polarization when we talked about critical angle. So that should be more than enough to get you all honky-dory on the homework. Have fun. I look forward to lecturing live as soon as we can. And thanks for your patience.